Hi, welcome Journey to the Confidential Cloud. My name is Russinovich. I'm Chief Technology Officer of Microsoft Azure. Now, back when I started in Azure, I recognized that a lot of customers were concerned about moving sensitive workloads and data to the public cloud. A lot of those fears have been allayed. The cloud has gotten much more secure, and many customers realize that the amount of investment in infrastructure security dwarfs what they can spend on their own infrastructure. And so ultimately, moving workloads to the cloud is resulting in a more secure posture than deploying them on premises. That said, customers are still looking for ways to minimize trust. And when you look at all of the scenarios for how data is being handled in a public cloud environment, and even on premises environments, there's concerns around data privacy, on untrusted collaboration between multiple parties. Regulation and compliance is requiring that data be managed and secured throughout its entire lifecycle. And then there's just customer trust in the environment that the cloud is operating for them. We've had for many, many years now data protection for when data is at rest and when data is in transit, and this is able to secure data through at least parts of its lifecycle. When data is at rest, customers now in public cloud environments can bring their own keys to have that data encrypted, and they can use common techniques like SSL and TLS to encrypt the data while it's in transit so that eavesdroppers on the network aren't able to see any data in clear text. Now that said, what's been missing up to this point is protecting the data while it's being computed on. If you look at a public cloud environment that a customer's trusting wholly when they place their data in the cloud, the application might load encrypted data from disk, but then it has to decrypt it while it processes it. And while it's in the clear then, in memory, in the CPU, it is technically accessible by the hypervisor, by physical operators of the data center that might get access to those servers, by malicious insiders that are performing DevOps on the infrastructure or even getting access to the customer's resources. Even multi-tenant breaches of hostile parties might end up getting access to the data while it's being accessed in the clear. What's been missing up to this point then is protection of data while it's in the clear, while it's in use. And that's what confidential computing is all about, is finishing off the protection of data so it is protected throughout and encrypted throughout its entire lifecycle, at rest, in transit, and finally while it's being computed on. And when we bring protection for data while it's in use, we actually end up opening up a lot of scenarios that have been very difficult to implement without this kind of protection. When you take a look at the scenarios I just talked about placing data in a public cloud, with data while it's protected in use, the data is now protected against malicious administrators, against hackers that might breach the multi-tenant boundaries, access from the cloud provider itself. But it also brings in to focus some other scenarios that have also been difficult, even in non-cloud environments, like protecting the user from their own data. Now you might be wondering, what does that mean? Why would you want to protect data from the owner of the data? Well, in many cases, the operators of the infrastructure that's processing data for a corporation or an organization should not have access to that data. While with now protecting that data while it's in use, we can technically assure that they don't have access to the data. Further, there might be data that is so sensitive that the company doesn't want to have humans ever seeing that data, only algorithms. And that is what confidential computing also makes possible. And then finally, one of the most exciting scenarios, for me at least, is being able to support multi-party computation scenarios, multi-party analytics, multi-party machine learning, where now you've got multiple parties that are able to bring their data together. They don't necessarily trust each other, and they might not even be able to merge their data sets together under normal circumstances because of regulatory restrictions. But with confidential computing, they can establish trust in the code and then share their data securely, knowing that only the code has access to the data, not the surrounding environment and not the other parties. But they all get access, or at least they can provide access to the output of a computation to authorized parties. In fact, With confidential computing, the public cloud can now effectively become like a private cloud. These environments that are defined by protection of data through its entire lifecycle, at rest, in transit, and now in use, supports these diverse scenarios you see listed here that require protection of data throughout its entire lifecycle. From financial services, where financial transactions have to be protected from the operators and from the environment around those transactions. In healthcare scenarios where you've got very sensitive data about patients that has to be protected and might even have regulatory requirements around protection of the data and access to the data. Now, with technical controls, you can enforce those regulations right in the code. And then finally, there's many scenarios where the government wants to provide services, but the government also wants to ensure the privacy of the citizens and ensure that only authorized parties have access to sensitive data about those citizens that the government is providing services for, like even in the healthcare space or taxation space. Those are all scenarios where trust in the code can provide these extra assurances that make citizens comfortable with having their data processed by these entities. And up to now, what we've seen to address these scenarios is private clouds, where there's air-gapped environments, where the infrastructure is obfuscated, and only certain people have access to those environments. Very complicated, very expensive. Confidential computing can effectively democratize private cloud on top of public cloud so that these various scenarios can take advantage of all of the network effects and economics of shared public cloud infrastructure, but yet with the assurances that are provided by effectively a private cloud infrastructure on top of it. In fact, we've seen lots of interest by organizations in those various categories that I just showed on the previous slide that are interested in taking advantage of confidential computing for those very purposes. One example is a collaboration between Microsoft and Scotiabank for multi-party data analytics of human trafficking, where multiple agencies are providing data. Those multiple agencies are curators of their own data and required through government regulations in Canada to protect the privacy of the data that they're holding. But yet, by merging their data sets with that of other agencies, they can get deeper insights into behaviors and financial transactions that might be reflecting human trafficking patterns that law enforcement then can take action on, with the privacy of the user's data being protected at all times. And another exciting scenario is a collaboration between Microsoft, Intel, and SAIL, the Secure AI Labs, where multiple parties are bringing together health care data sets and performing computations on top of those. Again, like I mentioned before, in these multi-party scenarios, they might not even be allowed to share their data sets with each other, but by combining them together, they can get deeper insights, and only the outputs of the data of the analysis are then made available. And this promises breakthroughs in the development of new drugs, also in the analysis of efficacy of treatments on patients, where the patient confidentiality is protected, the data sets of the different providers are kept confidential, but deeper insights about efficacy of treatment can be made available. So let's talk a little bit about what is the foundation of protecting data while it's in use. And it boils down to, of course, trusted execution environments, or TEEs, that minimize the attack surface. They provide boxes that are effectively black boxes as viewed from the outside. Inside of that black box, the data is decrypted and processed in the clear, but the box protects that data while it's in use from the environment around it. One example type of TE is known as an enclave, which is basically process level black box or confidentiality, where an application will carve out this enclave box into its address space, decompose itself into trusted and untrusted pieces, where only the trusted pieces should have access to the data while it's in clear, and therefore will execute inside the enclave. And then once that computation is happening there, the data is protected from all of those environments around it, the hypervisor, the operator, etc. Now, what is a black box? What is a TEE? Well, it consists of multiple capabilities, or requires multiple capabilities to be classified as a TE. Hardware root of trust is one, where cryptographically, at some point in the hardware, there's a key that effectively is the root of trust for that enclave. And that key is ultimately what is used to protect everything inside of that enclave. Another key component or foundation of a TE is the fact that it can remotely attest what it's running. So that CPU, that root of trust, is able to provide a quote that identifies the code that is running inside the black box so that somebody outside the black box can establish trust in that enclave and the code running inside of it. Trusted launch is also required. The ability to have policy that says only certain kinds of code can launch, and then that is secure launch combined with remote attestation, we end up with trusted launch. And then memory isolation encryption, it goes without saying that protecting that data while it's in use requires protecting the memory that data that is stored in, as well as the CPU state that is processing that data. And then finally, secure key management is a fundamental requirement where the code running inside that black box can protect its keys, store their keys securely. Remote attestation comes in various flavors. At the simplest form, something inside of the black box provides the quote, like I mentioned. The quote is signed by the CPU, and a third outside party to the black box can go verify that the quote was signed by the CPU by checking a public key that is registered somewhere. And typically this would be provided by an attestation service that has basically a registry of the public keys that correspond to the CPU's or the root of trust private keys. The quote comes out, and now a relying party can ask the attestation service and verify by looking at the public key, yes, this is a valid TEE, and so I can see what code is inside of that TEE and establish trust in it. Once I've established trust, I can then share secret data with it, provide it keys, for example, that will allow it to decrypt data. And another scenario is having the keys be stored outside the black box in a non-interactive manner such that the TEE launches, provides an attestation to a key management service that will verify according to policy whether a key should be released to the black box. And this is kind of the typical way we'd see an application leveraging TEEs is to store keys in a HSM that is protected by policies that say only TEEs that have certain code running inside them and are authenticated with root of trust that we trust and verify should have access to the keys to allow the TEE, the code inside the TEE, to decrypt the data. So these are the fundamental components of confidential computing. A TEE with secure launch, remotely attested launch, quoting, protection of the code while it's in use. And there are multiple types of TEs. I talked about enclaves as one example. And enclaves were basically made popular by ARM's Trust Zone and Intel's SGX, where you can see on the left side with Intel SGX an example of a trusted app with an enclave that has the trusted part of the app and the untrusted part of the app, like I just described, where the trusted part can then call into the enclave as required to perform a computation. That data is in the clear, only inside the enclave, and then it provides results out to the untrusted part. And those results can even be encrypted such that only a client that is authorized to have access to those results can see them. And in that case, the trusted app is just a proxy for the enclave. But more recently, both Intel and AMD have launched confidential virtual machines. And confidential virtual machines provide an entire environment where you can take an off-the-shelf operating system and run it completely inside of the TEE. In this case, it's running on top of a hypervisor. The hypervisor does not have access to what's inside the virtual machine. And AMD started down this path with AMD SEV and now AMD SMP virtualization, where the entire state of that virtual machine, from the CPU registers to the memory, is protected and encrypted by the CPU, and of course can provide the same kinds of quotes that I described earlier as a foundation for a TE. Now, when you take a look at the spectrum from enclaves to confidential virtual machines, you end up with a confidential computing programming spectrum, where on the far right you've got enclaves. There's programming models like the Open Enclave SDK that make it easier to interact with the features of the TEE, like the quoting, for example, and providing the ability for code applications to be able to create enclaves and interact with them. But in those cases, because you're working with process level isolation that doesn't have, for example, privilege levels, you need to port code into that environment. You can't take an off-the-shelf operating system, general operating system code, and just run it. The benefits of that, though, for the reduced surface area is that the TCB is much smaller. Now, one of the concerns that you still have to worry about when you're developing confidential applications are side channel leakage and vulnerabilities inside the code. So the more code you put inside of the TEE, the more potentially vulnerable you are because the larger the surface area. So on the far right, you restrict the TCB, you put a minimal set of code in there by porting the code into that environment, and now you've got higher assurance that the code is going to be, the data is going to be kept confidential. You can also see that there's custom frameworks that support the use of enclaves for specific types of program models, like the Confidential Consortium Framework, or CCF, which provides blockchain capabilities in a network of TEEs, such that that network arrives at consensus, can log transactions in an immutable manner, and perform it all confidentially, so that only certain transactions or the results of them are available to certain customers or clients. Now, when you move over to the left side of that spectrum, that's when you start to get more and more compatible. Like confidential containers, you can be able to effectively lift and shift a container application, containerized application, and run it. So on top of a framework or an orchestration system like Kubernetes, now you can get confidentiality. This is slightly different than having a container launch an enclave that is confidential. In this case, the whole container itself is launched in the confidential environment. And then, of course, I mentioned on the on the previous slide about confidential virtual machines. Now you can take and store or launch entire operating systems off the shelf inside the confidential virtual machine. Of course, at that point, the TCB is much, much larger. You're having to trust all of the kernel code and user code that's part of that operating system. But you get this very rich environment to host applications with no changes. And so where you choose to land on this spectrum really depends on what kind of code you got, how portable is it, can you make it work inside of an enclave, how compatible do you have to be, and what is your risk level for that increased TCB as you go over to the left side of this diagram. The bottom line is that there's no one-size-fits-all answer here, and it really depends on the requirements of the application and the constraints of the code that application is built on top of. But this picture is just going to get richer over time, and you might see other points on this spectrum emerge as time goes on. Now let me switch to talk a little bit about confidential computing inside of Azure. And I'll start by saying that confidential computing in Azure has been a long journey. I mentioned that back in 2014, as I was thinking about customers bringing their sensitive workloads to the cloud, and I discovered the research that was going on in Microsoft Research on confidential computing, I recognized that confidential computing could be a way to make customers more comfortable with moving data into the public cloud. And we've been on a long journey since, with Microsoft Research helping us develop confidential computing technologies, working with partners in the hardware ecosystem to push forward and make confidential computing hardware more general purpose, remove the performance restrictions that it has, and end up in these larger TEs that are more compatible, like I mentioned. A few years ago, we were a founding member of the Confidential Computing Consortium to help push forward the whole industry into developing confidential computing solutions that we could all take advantage of. Open Enclave SDK is one of those examples that we contributed to the CCC. Our belief being that the Open Enclave SDK, as a way to create a plug-in model for different types of enclaves, would make it easier for developers to take advantage of enclave technology. Without having to customize their code for each individual enclave, they could write enclave generic code that could then be deployable to, for example, Intel SGX or TrustZone or other enclave technologies as they emerge. And we've seen resounding interest in confidential computing for the obvious reasons that this is kind of a turning point in the evolution of computing and secure computing. And you can see the general members there and the premier members that reflect a diverse set of ISVs, hardware vendors, and cloud providers, all now contributing to this industry-wide momentum on evolving confidential computing. The Confidential Computing Consortium has only been in existence for a few years. We're still very early on this journey, and there's so much more to do, but it's really exciting to have such a large ecosystem now developing to advance confidential computing. Microsoft itself continues to advance confidential computing as well. We're developing our own services and making confidential computing hardware directly available to customers. So if you start with just the hardware, the foundations, the TEs themselves, we've been working with Intel, we've been working with AMD, and we've been working with ARM. And you can see that we support all of these hardware technologies provided by these different vendors right now and or in preview. Intel SGX, like I mentioned, with first Cascade Lake and now Ice Lake SGX. We've got AMD in preview, and we've got Trust Zone support. And on top of these, we make them available to our customers in the form of virtual machine and edge offerings. And you can see virtual machine offerings like our DCS V2 and DCS V3 virtual machines, our EC and DC V5 or DCA and ECA V5 virtual machines that are SNP virtual machines. We've also, as a fundamental requirement, I mentioned Trusted Launch as a key foundational component of TEs. We've built Trusted Launch, which is secure launch and attested launch, combination of those into our general purpose virtual machine fleet. And that's a GA capability, so you can have an Azure virtual machine that launches and then attests to the fact that it's launched using virtual TPM technology. And then finally, we also support SGX enclaves and ARM Trust Zone enclaves with our IoT edge solutions. That is the hardware foundations made available as offerings to our customers. And on top of this, we've been developing confidential infrastructure services that make it easier to develop confidential applications. I mentioned remote attestation earlier, described it. Well, we have a Microsoft Azure attestation service that provides attestation tokens that verify the authenticity of the quotes that are coming from SGX or SMP hardware that can also be augmented with other claims. And so we see this getting richer over time. The capabilities of Microsoft Azure attestation claims that can be augmented to specify what versions of software are running inside those enclaves, what geolocation that hardware is positioned in. So if there's data sovereignty requirements, that can also be reflected and verified through the claims coming from Microsoft Azure attestation, either directly by a client that's interacting with a TE or by our Azure Key Vault Managed HSM service, which has a capability built into it called Secure Key Release. And with Secure Key Release, you can specify policies, as I described before, on when an HSM key should be released to a TEE, such that it might only be releasable to a TE that is running with a specific version of firmware, with a specific code, and a specific location. And so Azure Key Vault Managed HSM is also a service that will continue to evolve over time to be richer in terms of the policies that it supports. And then on top of that, we're building confidential services. So these layers from hardware now to infrastructure service to confidential services that include PaaS capabilities like Azure SQL Always Encrypted, which leverages SGX enclaves to run the SQL query processor inside the enclave. What that does is it isolates and protects the data of the database such that the customer themselves operating that database can't necessarily get access to it unless they're authorized access to it. The Microsoft operators of the Azure SQL infrastructure don't have access to it. The hypervisor doesn't have access to it. DevOps personnel doesn't have access to it. It's protected by that SGX enclave. We also have confidential inference support in the Onyx runtime. So the Onyx runtime has been ported to run inside of SGX enclaves. So now you can store a machine learning model inside the enclave. It's protected from the outside, and the data that it is performing inference on is also protected end to end. So a client establishes a trusted connection, a confidential connection with the enclave that has the inference model inside of it, can send the data into it and get back the results, again, protected completely from the outside environment. We also have Azure Edge IoT with Enclave, so you can run IoT Edge runtime inside of an SGX Enclave or Trust Zone Enclave. And then finally, we have a confidential ledger service. I mentioned CCF before. CCF underlies our confidential ledger service, which provides you immutable, tamper-proof logs on the ledger. And at some point, this will be opened up to be fully decentralized in capabilities so that you can run nodes outside of the Azure environment. So again, these are the foundations we've been building up over time, and we're continuing to invest on this and creating richer and richer. You'll see more services. You'll see these services become more capable over time. And this is just early stages for Microsoft's investments in confidential computing. Now, I'd like to share with you a demo because I mentioned earlier that we've been working with many customers. Many customers are developing solutions on top of Azure, even outside of Azure. But this demo that I'm going to present to you really reflects the multi-party computation scenarios that I described earlier, actually running on side of Microsoft confidential enclaves in Microsoft's cloud. In this fictitious scenario, it's similar to the fraud detection scenario. We've got two banks. They want to combine their data to perform fraud analytics on that shared data set rather than each of them performing it individually and not having insight into potentially the transactions that might only surface as fraudulent when they're combined with the data from and the transactions data from another bank as transactions move between them. In this case, we're running on top of Graphene, which is a project, open source project contributed by Intel to the CCC that provides you a POSIX operating system environment inside of an SGX enclave, making it easier to port code into the SGX enclave. And that's what we took advantage of here to perform machine learning training inside of the enclave. Now here you can see I've got three windows. On the rightmost window, I'm logged into an Azure virtual machine that has SGX capabilities. I'm not actually in the virtual machine. I'm in what will be representing as the untrusted part of the application, where the trusted part is going to run in an SGX enclave. On the left side, I'm logged into two different banks environments, and each bank environment has their own private data sets, and where those private data sets are going to be analyzed and combined for fraud detection. Now, to show the benefits of combining those data sets, I'm going to perform the fraud analytics inference detection on top of that first bank's data set, and you can see that I've got a precision of about 92.7%. And you can see that I've got clear text data here when I take a look at that file that was sent into the fraud detection algorithm. There's sensitive data that we want to protect from access by the cloud provider as well as the other bank. I'm going to encrypt the data, and when I encrypt the data, you can see that the clear text is gone and the results are obfuscated. Now I'm going to upload that encrypted file to that confidential virtual machine, and then flip over to Bank 2, where we're going to take Bank 2's data set, encrypt it, and then upload it. And now at this point, if you take a look in that confidential virtual machine, I'm in the untrusted part of the application. So when I try to look at those files, of course, I'm just going to see the encrypted data and not the encrypted data. Now I've also got copies of that data in unencrypted form that I can perform the fraud analytics on top of. Again, this is going to be a fraud analytics computation that is on that combined data sets. And you can see that we end up with a precision of over 98%. So significantly higher than this Bank 1's own fraud detection on its own private data set. And because I performed that computation in the clear, I've got another window open to the left on that same virtual machine, which can look at the process list, see the demo process, which is where that computation is happening, and then perform a dump of its memory contents and see the data in the clear. So in this case, I'm just showing that if we uploaded those encrypted data sets, then provided those keys to the virtual machine, those virtual machine process the data using the fraud analytics algorithm, that it would be accessible to anybody in that environment on the virtual machine, like a Azure DevOps op personnel, to somebody that breaches the infrastructure. I'm going to run that same computation now inside the SGX enclave. You can see that I'm launching Grameen SGX. And at this point, now only the SGX enclave will have access to the keys to process it in the clear. We get our same precision score. But now when we go back and take a look at the process list, we can see the demo process, but the demo process, which has the enclave as part of its address space with that data encrypted in it, now shows up as not having any sensitive data that can be seen from the outside. So this demo shows the very standard kind of model of two parties having sensitive data, not even needed to perform complex obfuscation and data cleansing, but being able to provide that sensitive data as is into the confidential environment where only the code inside of the SGX enclave has access to it. And the results are made available now to those parties for better insights into the data. So that is a real look at the kinds of exciting scenarios with multi-party computation that are starting to emerge. And there's ISVs, some of you among them, that are starting to build frameworks and tooling to support confidential multi-party computation, which I think is a huge, very exciting area for confidential computing to really light up. Now, I'm convinced more than ever. I was convinced in 2014 that confidential computing was going to become the future of computing in general, not just Microsoft Azure's cloud. We had an obligation to our customers to drive forward confidential computing. The fact is, the future is going to be confidential. And I mentioned that the CCC was formed just a few years ago, but just during that time, the awareness of confidential computing has really exploded. Last year, I kind of view as a breakthrough year in confidential computing, both in terms of general awareness by the industry, the momentum that the CCC reflects, as well as the bringing to market by AMD of confidential virtual machines to really make it much easier to make applications confidential. And the CCC funded a research project by the Everest Group to look at the market, and you can see that the Everest Group has come back and said that they expect the addressable market for confidential computing to really exponentially grow over the next 5 years to an over $50 billion market. And I think this is just really the beginning. What you're looking at here in this very near term, given still the performance overheads and the complexity of setting up and the lack of rich tooling for setting up confidential computing applications and operating them, that we're really seeing the tip of the spear, the most sensitive workloads that are really now being enabled with confidential computing to driving this. But the fact is, as confidential computing becomes more ubiquitous, as the tooling gets richer, as the performance overheads go away, and confidential virtual machines, for example, become available inside of every infrastructure. So flipping a switch and saying whether it's confidential or not becomes something as easy as just setting a switch on a virtual machine, and you see no performance degradation. What we're ending up heading towards is a fully confidential cloud. The infrastructure will be confidential. The services on top will be confidential. The records of what happens will be immutable and auditable and confidential. And ultimately, the cloud platform will be leaving the trusted compute base, the TCB, of customer applications, such that trust in the public cloud and the infrastructure is minimized. And we're ending up in a trustless world of confidential cloud. And it won't just be for sensitive workloads. It will be for every workload. Just like over the last few years, we've seen the standard adoption of encryption while data is in motion. We'll see an expectation that data is always encrypted while it's in use, regardless of how sensitive it might be. It'll just be the default posture for secure computation. So with that, I want to thank you for inviting me to keynote this event. It's exciting to see such industry excitement from everybody here representing the hardware ISVs, the IHVs, as well as the cloud providers, interested in driving forward together confidential computing and creating these solutions that will help customers have their data be protected throughout its entire life cycle. The future of the cloud, the future of computing is confidential. Thank you very much.